Let us continue with wave optics part 6. Consider two waves interfering at a point. We understand this by the principle of superposition of light waves. When two or more waves arrive at a point simultaneously, each wave produces its own displacement at that point independent of the other. The resultant displacement at that point is equal to the vector sum of the displacement due to each wave at that instant. Y vector is equal to y1 vector plus y2 vector. If y1 and y2 are the amplitudes of each wave, either crest and crest can come together, or a trough and a crest, or a crest and a trough, or a trough and a trough at that point. The amplitudes are as shown. So in the first one, crest and crest gives you y1 plus y2. One trough and one crest gives you minus y1 plus y2. The crest and the trough gives plus y1 minus y2. And trough and the trough gives minus y1 minus y2. If y1 is equal to y2 is equal to y, the amplitudes are same. All these are capital Y. You get it as 2y, 0, 0 and minus 2y. The crest and the trough gives you what is known as the constructive interference. And the zeros gives you the destructive interference. Constructive interference, when two waves, two sources of light, are in phase, that is the path difference between them is an even integral multiple of lambda by 2, then we get constructive interference. Path difference is equal to 2n. 2n implies even number. 2n lambda by 2. So 2 gets cancelled. You get n lambda. That is n equal to 0, plus minus 1, plus minus 2, plus minus 3 because they are on both the sides. Since phase difference is equal to 2 pi corresponds to the path difference lambda. Phase difference delta phi n is equal to n into 2 pi. See, we have replaced lambda by 2 pi where n is equal to 0, plus minus 1, plus minus 2 and so on. The point is bright. Destructive interference. When the two sources of light are in opposite phase and the path difference is odd integral multiple of lambda by 2, the path difference is equal to n minus half. See, here it is an odd number, n minus half times lambda, where n is equal to plus minus 1, plus minus 2, plus minus 3. Phase difference, delta phi n is again n minus half, 2 pi, where n is equal to plus minus 1, plus minus 2, plus minus 3 and so on. The point is dark. Young's double-slit experiment comprises of a source S which gives rise to S1 and S2 on a cardboard with two holes, gives out spherical wavefronts which reaches the screen and gives you an interference pattern. That's the waveform associated with it. So this is the thing that is observed on the screen. Thomas Young was the first to demonstrate interference of light waves. A beam of light is allowed to pass through S. The light emerging from S is allowed to pass through two more pinholes S1 and S2 very close to each other. Thus the sources S1 and S2 are obtained from the primary source S. Hence they act as coherent sources and gives rise to spherical wavefronts. This is the front view of the Young's double-slit experiment. These are the interference fringes, we call it, the alternate bright and the dark bands. Importance of Young's experiment. It was the first experiment in which the interference of light was observed. It proves that light is propagated in the form of waves. It can be used to determine the wavelength of a monochromatic light. Young's experimental observation. Interference fringes are produced in the region where the two waves overlap. If the source slits S1 and S2 are made narrow, the fringe width is unaffected but the intensity increases. If the distance between S1 and S2 is diminished, the bandwidth increases, S is fixed. If the source slit S is widened, the fringe gradually disappears. Slit width S must be less than lambda d by d, where capital D is the distance of the screen from the two sources S1 and S2. If either S1 and S2 is closed with a finger, fringes will disappear. If white light is used, the central fringe is white and the fringe on either sides are colored. Blue is the color near the central fringe and red is away. Let's treat the interference bands analytically. So S1 and S2 are the two coherent sources separated by a distance small d from which the wave starts and fades. Join S1p and S2p. D is the distance from the source to the screen. Y is the distance of P from the central bright fringe. Path difference delta L is equal to S2P minus S1P. Now let's apply geometry to this double slit experiment. From the diagram, we apply Pythagoras theorem to the triangle S2BP and S1AP. We get S2P square is equal to S2B square plus BP square. That is equal to capital D square plus Y plus D by 2 the whole square. S1P square is equal to S1A square plus AP square. That is equal to capital D square plus Y minus D by 2 the whole square. Subtracting equation 2 from 1. S2P square minus S1P square is equal to capital D square plus Y plus D by 2 the whole square minus capital D square minus Y minus D by the 2 whole square. We get it as 2YD. So S2P minus S1P into S2P plus S1P, we apply the function A square minus B square is equal to A plus B into A minus B, that gives out 2YD. S2P minus S1P is equal to 2YD upon S2P plus S1P. Since Y is much less than capital D and the distance between the two slits small d is much less than capital D, D by D is much less than 1. S2P and S1P are almost same, so we can write it as 2D. Therefore, S2P minus S1P is equal to 2YD upon 2D. S2P minus S1P is equal to 2YD by D. S2P minus S1P is the path difference between the two waves. For the end fringe, the path difference delta L is equal to Yn small d upon capital D. If point P is bright, delta L is equal to Yn d by d, that is equal to n lambda, where n is equal to 0 plus minus 1 plus minus 2 and so on. Yn is equal to n lambda d by d. If the point P is dark, then delta L is equal to Yn d by d minus n minus half lambda, where n is equal to plus minus 1 plus minus 2 and so on. Yn is equal to n minus half lambda d by d. Now let's talk about the fringe width. The distance between the two consecutive bright or dark bands is called the fringe width. For bright bands, y is equal to yn plus 1. See, consecutive yn plus 1 minus yn. That is equal to n plus 1 lambda d by d minus n lambda d by d. So that comes out to be w is equal to lambda d by small d. For dark bands, w is equal to again yn plus 1 minus yn dark. That comes out to be n plus minus half lambda capital D by small d minus n minus half lambda d by d. So w again comes out to be lambda d upon small d. From 5 and 6, the distance between two consecutive bright bands is equal to the distance between the two dark bands. Therefore, the fringe width is equal to w lambda d by d, whether it is bright or dark. The relation between the path difference delta n and the phase difference delta phi is equal to delta phi is equal to 2 pi by lambda into delta L. Thus, the phase difference between the two waves reaching P from S1 and S2 is delta phi is equal to 2 pi by lambda yd by d. We substitute for delta L as yd by d. Now, let's talk about the intensity distribution. I naught is directly proportional to E naught square, where I naught is the intensity of the incident wave. The two waves coming from S1 and S2 mathematically follow the sine function with the amplitude E naught. Therefore, E1 is equal to E naught sine omega t and E2 is equal to E naught sine omega t plus phi. E is equal to E naught sine omega t plus E naught sine omega t plus phi. Well, that is equal to, we use the trigonometric functions, that gives you 2 E naught cos phi by 2 into sine of omega t plus phi by 2. Thus, E is a sine wave having an amplitude 2 E naught cos phi by 2. Intensity is proportional to the amplitude. The amplitude is 2 E naught cos phi by 2 the whole square. So, intensity is proportional to 4 E naught square E square phi by 2. That comes out to be 4 into I naught. We know that E naught and I naught have the relation as shown above. That is equal to 4 I naught cos square phi by 2. If E10 and E20 are the two amplitudes now of the two waves, then at the center of the bright fringe, the intensity will be proportional to E10 plus E20 square. At the center of the dark fringe, the intensity will be proportional to E10 minus ET0